Hi students, this is our third lesson for the topic of complex numbers for the International Baccalaureate course, Analysis and Approaches. In this video, we're going to look at geometry in the complex plane. Now, as we've learnt, imaginary numbers cannot be represented on a real number line. So instead, we represent complex numbers on a complex plane, and this is also called an Argand diagram. The x-axis represents the real part of the complex number, and the y-axis represents the imaginary part. So in this example, the points -3, 2, 2, 1, 3, -1, and 0, -2 represent the complex numbers -3 plus 2i, 2 plus I, 3 minus I, and -2i. Complex numbers can also be represented as vectors from the origin. So this complex number a plus bi can be represented by the vector OP. Example 1, if z1 is equal to 3 plus I and z2 is equal to 1 plus 2i, represent z1 plus z2 on the complex number plane and describe the result geometrically. So z1 plus z2 is equal to 4 plus 3i. When we plot that, we get the diagonal of a parallelogram. Now that parallelogram that happens when we add two vectors has some important features. Firstly, we can talk about the diagonals. So we just saw how this diagonal here is the addition of the two complex numbers. And if we take the modulus of that addition, then we have the length of that diagonal. If we have a look here at this other diagonal, if the vector points in this direction towards z1, then that's the vector z1 take away z2. And if we take the modulus of z1 take away z2, we have the length of this diagonal. But here's an important point. The distance between two complex numbers z1 and z2 is going to be given by the modulus of z1 take away z2. And one more result from the parallelogram. Since the diagonals of a parallelogram bisect one another, we have the following result. The vector OM is equal to half of z1 plus z2. And M is going to be the midpoint of AB. And this leads us to two really important triangle inequalities. The first one states that the modulus of z1 plus z2 is always less than or equal to the modulus of z1 plus the modulus of z2. The second one states that the modulus of z1 minus z2 is always greater than or equal to the modulus of z2 take away the modulus of z1. Now I encourage you to substitute some numbers in and convince yourself that they're both true. You might even want to look at the proof. And then ask yourself this question: what happens if there is equality in these situations rather than an inequality? And example 2, if z is equal to 1 plus 2i, show iz, I squared z, I cubed z, and I to the power of 4z on the complex plane. And it looks like this. So here's z, this is iz, I squared z, I cubed z, and then here is I to the power of 4z. So here's an important point. Multiplying by I is equivalent to a quarter turn anti-clockwise about the origin. And you might enjoy this t-shirt. Sorry, you have reached an imaginary number. If you require a real number, please rotate your phone by 90 degrees and try again. Now, graphically, the conjugate is a reflection of the complex number z in the real axis. So here we have x plus yi, and here's the conjugate x minus yi. Okay, let's move on. The locus of a point is the path through which it moves whilst obeying certain conditions. If you have a look there at the animation, the path that has been traced out by the bottom of the swing there is an arc of a circle. Now in this course there are three main types you need to be aware of. fixed distance from a straight line is going to be a straight line. So for example, if a point is always 3 units to the right of the y-axis, then it's going to be this vertical line here, x is equal to 3. Fixed distance from a point is going to be a circle. Here's an example. The point is always 3 units from the origin. Equal distance from two fixed points is the perpendicular bisector of the line segment that joins the 2 points. Here's an example. The point is equidistant from two fixed points, 1, -2 and 3, 4. Let's finish off with some examples. Sketch and describe the following subsets of the complex plane. So here we have the modulus of z is equal to 1. Now remember that this is the distance that z is from the origin, and that's always going to be equal to 1. So this is a circle. It has centre at the origin, and the radius is 1. So imagine that your complex number is on this circumference of the circle, always 1 unit away from the origin. B. The modulus of z is less than 4. So again, we have a circle centered at the origin. The radius is 4, but this circle is going to be colored in, and because we don't have equality here, it's going to have a dashed line on the circumference. This one is not centered at the origin. The center is 1 plus I, so this means the distance that z is from the point, 1 plus I, is always going to be less than or equal to 2. So again, it's a region inside a circle. This time it has a solid circumference because we have an equality sign, and the radius is 2. D. Modulus of z is equal to the modulus of z plus 1 minus 2i. Now I'm going to change this one slightly so that we're representing a distance between 2 points. Now this is saying the distance that z is away from this point must always be equal to the distance that z is away from the origin. So that's the perpendicular bisector of the line segment between those two fixed points. E. Argument of z is equal to pi on 6. So this looks like this. From the positive x-axis, z is going to lie anywhere on that ray because that has an angle of pi on 6 from the positive x-axis. Now really importantly, we have an open circle at the origin because z can't equal 0 plus 0i and still have an argument of pi on 6. In that case it would have an argument of 0. But z can lie anywhere else on that ray. And of course it might be in reference to another point like this one. Argument of z take away in brackets 2 plus I must be equal to negative pi on 4. So this time our point of reference is 2 plus I. We take the positive horizontal and then we want an argument of negative pi on 4. So z can lie anywhere on this ray, but of course not at the point 2 plus I. And G. The real part of z plus the imaginary part of z is equal to 3. Now this one looks complicated, but it's actually the easiest of all of them. The real part of z is x, the imaginary part of z is y, so this is just a straight line. So just a couple of things to remember. Complex numbers can be interpreted algebraically or geometrically. Modulus of z is equal to the square root of x squared plus y squared. It's the distance from the origin to the point xy. The modulus of z take away a plus bi in brackets is the distance of z from the point AB. Arg z is the angle from the positive real axis in an anti-clockwise direction to the vector z. And finally, arg z minus z1 is the angle from the positive horizontal line y is equal to the imaginary part of z1 in an anti-clockwise direction to the vector z minus z1. Okay, that's it. In our next video, we're going to look at representations of complex numbers.